In this video, we will see how the ellipsoid method can be used to solve some linear programming problems with exponentially many constraints in polynomial time. We're not going to see the details of this variant of the ellipsoid method, but we're only going to describe the main ideas. After that, we will also discuss one example. As always, we consider the linear programming problem of minimizing C transpose X subject to AX greater than or equal to B. We assume that the dimension of A is m times n, and without loss of generality, that the entries of A and B are integer. Now we know that the ellipsoid method is able to solve this linear programming problem in a number of iterations that is polynomial in n and log u. The key observation here is that m plays no role in the number of iterations of the ellipsoid method. So the number of iterations is independent of the number m of constraints. This suggests that we may be able to solve, in time polynomial in n and log u, problems where the number m of constraints is huge, for example exponential in n. As we will see, this turns out to be possible in several cases. However, we need to make some assumptions. In fact, it is really simple to see that we need some assumptions. Suppose that m is exponential in n, for example that m is equal to 2 to the n. This means that our matrix A has 2 to the n rows, and so it takes exponential time only to read our input matrix A. And if we're not able to even read our data matrix A, then for sure we will not be able to solve our linear programming problem. So then, obtaining an algorithm which is polynomial in n is clearly impossible in general. The way around this problem is to assume that our system AX greater than or equal to B is not given explicitly by listing all the entries in A and in B. Instead, we will assume that our system AX greater than or equal to B is given in a concise way. This sounds very strange, so let me give you immediately an example. Consider the following set of constraints. Sum of ai xi for I in S is greater than or equal to cardinality of S. We consider this inequality for all subsets S of 1 to n. So in total, this system contains 2 to the n constraints. However, I am able to give them to you in a very concise form. In fact, everything I need to tell you is their form over here, and I need to give you the n scalars a1 until an. We are now ready to state our first assumption. We only consider linear programming problems of the form minimize C transpose X subject to X in P. Here, P must be a polyhedron with a very special structure that we now formalize. Our polyhedron P must be described by specifying first its dimension n and then an integer vector age of primary data. This integer vector must be polynomially small. That is, it must be of dimension big O of n to the k, where k is just a constant. In the example that we have just seen, we have that our vector of primary data consists of all the coefficients a1 until an. So this vector has only n entries, and so we have k equal to 1. So now we have our primary data, and we need a way to be able to understand the original system from the primary data. So we need to have some mapping which, given n and age, defines our system of constraints AX greater than or equal to B defining the polyhedron P. In particular, no restriction is placed on the number of rows of A. Let me remark that when you have n, age, and the mapping, in principle you're able to construct the system AX greater than or equal to B. Of course, we will not do this, because again, writing down explicitly the system AX greater than or equal to B in general requires exponential time. At this point, we're not yet done with our first assumption. This is because the runtime of the ellipsoid method depends on u, which is an upper bound on the absolute values of the entries of A and B. So if we hope to obtain a polynomial time algorithm, we need to guarantee that log u is polynomial in the size of our primary data. To do so, we let u0 be the largest absolute value of the entries in our vector of primary data age. And as always, we let u be the largest absolute value of the entries in A and B. Our last assumption is that log u is polynomially bounded by n and log u0. Formally, we assume that there exist constants c and l such that log u is upper bounded by c times n log u0 to the power of l. Now let's immediately see how we use this assumption. Now the size of an instance of our problem, as described using the primary data n and age, is big O of n to the k log u0. This is because the vector age has big O of n to the k entries, and each one is at most u0 in absolute value. Now let's apply the ellipsoid method to our problem. And for now, let's just focus on the number of iterations. The number of iterations is big O of n to the 6 log nu. This is simply big O of n to the 6 log n plus n to the 6 log u. Now we use our assumption that says that log u is big O of n log u0 to the l. We obtain that big O of n to the 6 log u is big O of n to the 6 plus l log of u0 to the power of l. Clearly, this is polynomial in the size of the primary problem data, which we saw is big O of n to the k log u0. So now are we done? Do we have an algorithm which is polynomial in n and log u0 for our special class of polyhedra? Well, not necessarily, because so far we have only analyzed the number of iterations. We haven't yet analyzed the computational complexity of a single iteration. So now let's look at the detail of a single iteration. If you go back and check a typical iteration of the ellipsoid method, you will see that there are only two differences from the case where P is explicitly given by a system AX greater than or equal to B. These differences are in step 2, part B and C of the main iteration. In our iteration, we are at the point where we have our ellipsoid with the center xt. In step B, we check if xt is in P, and if so, we stop, returning that P is non-empty. Otherwise, it means that xt is not in P, and we need to find a violated constraint. So an inequality from the system AX greater than or equal to B that is violated by xt. Now previously, when we had explicitly the system AX greater than or equal to B, both these steps were accomplished by examining each one of the M constraints. Everything we had to do was to plug in the vector xt and check every single constraint. If all of them were satisfied, we knew that the xt was in P, otherwise we knew that xt was not in P, and this is because we found the constraint violated by xt. Now, in our new setting, this approach is no longer viable. In fact, if m is exponential in n, checking if xt satisfies all the constraints would result in an exponential time algorithm. So being able to carry out these steps is the key to obtain a polynomial time algorithm when m is large. These steps are so important that they have their own name. The name is the separation problem. Let's define it formally. Given a polyhedron P in Rn and the vector x in Rn, the separation problem is to either decide that x is in P or find a vector d such that d transpose x is strictly smaller than d transpose y for all y in P. In other words, in point P, we wish to find a separating hyperplane, which, as we have seen in chapter 4, is a hyperplane such that P lies on the one side and the vector x lies on the other side. I'm sure you've noticed that there is a small difference between the separation problem that we just defined and steps 2b and 2c of the ellipsoid method that we saw a couple of slides ago. In fact, in the case when the vector is not in the polyhedron, the ellipsoid method asks for a separating hyperplane among the constraints in the description of P. On the other hand, the separation problem asks for any separating hyperplane. It turns out that this difference is of no significance. In fact, it can be easily checked that the ellipsoid method also works in the same way if, in step 2c, we obtain any separating hyperplane instead of one among the constraints in the description of P. So now let's assume that we can solve the separation problem in time polynomial in n and log u. Soon we will see that this is indeed sometimes possible. If this happens, then the number of operations performed in each iteration of the ellipsoid method is polynomial in n and in log u. Since we have already seen that the number of iterations is also polynomial in n and log u, we obtain that the total running time of the ellipsoid method is polynomial in n and log u, and therefore polynomial in n and log u0. We obtain the following key theorem. If we can solve the separation problem in time polynomial in n and log u, then we can also solve linear optimization problems in time polynomial in n and log u. Furthermore, if our previous assumption that log u is less than or equal to Cn to the L log of u0 to the power of L, then the running time is also polynomial in n and in log u0, and therefore polynomial in the size of our input. Essentially, this theorem states that if you can solve the separation problem in polynomial time, then you can also solve the optimization problem in polynomial time. Interestingly, it can be shown that also the converse holds under some technical conditions. So the separation problem and the optimization problem are polynomially equivalent. Formally, we can solve the separation problem in time polynomial in n and log u, if and only if we can solve the optimization problem in time polynomial in n and log u. Now let's see an example. We look at the traveling salesman problem. This is one of the most famous problems in combinatorial optimization. In this problem, we have in input a non-directed graph G equal to NE with n nodes. We are also given edge costs CE. The goal is to find a tour of minimum cost, and the tour is defined as a cycle that visits all nodes. In the picture, we have an example of an optimal tour passing through the 48 continental state capitals. In this example, the edge costs are given by the distance among two capitals. How can we formulate this problem as an integer programming problem? We introduce a variable xe for every edge. Xe will be equal to 1 if the edge e is included in the tour, and it is equal to 0 otherwise. To write down the formulation in a nice way, we define delta of S for every subset S of nodes. Delta of S is the set of edges that have one node in S and one node not in S. In particular, this means that delta of a set containing only one node is the set of edges incident to that node. Now let's discuss the constraints of our integer programming problem. Clearly, in every tour, every node is incident to two edges. So for every node I, we write that the sum of xe for every edge e incident to I is equal to 2. However, you can check that these constraints are not sufficient to obtain a formulation of the traveling salesman problem. To obtain a formulation, we need to introduce another set of constraints. To understand these constraints, think about partitioning all the nodes into a set S and a set of the remaining nodes n minus s. Now assume that there exists at least one node in S and at least one node in n minus s. Then, eventually, your tour will pass by the node in S. Then your tour somehow will have to get to the node in n minus s. And later on, it will have to somehow come back to the node in S. This means that there must be at least two edges in the tour connecting S and n minus s. We write these constraints as the sum of xe for e in delta of S greater than or equal to 2. And this constraint should hold for every subset S of n, such that S is non-empty and is also different from n. It's a good exercise for you to check that the constraints that we have written down so far, together with the binary constraints on the variables, gives a formulation of the traveling salesman problem. Now we write down the linear programming relaxation of the integer programming formulation of the traveling salesman problem. Our objective is to minimize the cost of the tour, so we minimize the sum of CE xe for every edge e. Then we have our first set of constraints, and then our second set of constraints. Finally, we relax the binary constraints on xe with the constraints xe between 0 and 1 for every edge e. Of course, this linear programming problem will not solve the traveling salesman problem. However, solving this linear programming problem provides a lower bound to the optimal cost of the traveling salesman problem. Now note that this linear programming problem has exponentially many constraints. In fact, in our second set of constraints, we have a constraint essentially for every subset of n, and this number is 2 to the n. From our previous discussion, if we are able to solve the separation problem in polynomial time, then we can also solve this linear programming problem in polynomial time. So we now show that the separation problem can be solved in polynomial time. What do we have to do in the separation problem? We are given a vector x star and we need to check if it is feasible. So we need to check if it satisfies all our constraints. If it doesn't, we also need to return a violated inequality. Now, some of the constraints we can directly check because they're just polynomially many. These are our first set of constraints because we have one for every node, so only n of them. And we can also check in polynomial time whether every component of x star is between 0 and 1. These are an additional 2m constraints because I have 2 constraints for every edge. So in total, I can check this n plus 2m constraints directly by simply plugging in x star. If I find any violated constraint among these ones, then I'm done because I know that x star is not in my polyhedron and I've also found a violated constraint. So let's now assume that x star satisfies all these constraints. We still have to check the remaining constraints, which I've written down once again over here. What we do now is we search for the subset S of n, different from the empty set n from n, that minimizes this sum over here. We call this sum C of S. We will denote by S0 this set that minimizes C of S. Now it is well known that S0 can be found in time polynomial in n. In this course, we have never discussed this problem. However, this problem is known as the minimum cut problem, and it can be shown that it is equivalent to solving a maximum flow problem. Okay, so now if you believe me, it is possible to find the set S0 minimizing this sum in polynomial time. Now, why did we want to find this set S0 in the first place? There are 2 cases we're going to discuss. The first is that C of S0 is greater than or equal to 2. In this case, then we can argue that the point x star is feasible. Because if C of S0 is greater than or equal to 2, it means that the smallest among these sums is greater than or equal to 2. And this implies that all these sums are greater than or equal to 2. So the point x star satisfies all these constraints and it is feasible. The other case is when C of S0 is strictly smaller than 2. This means that this sum corresponding to the set S0 is strictly smaller than 2. Therefore, the inequality corresponding to S0 is violated by x star. So we have understood that we can solve the separation problem in polynomial time. Therefore, if we now apply theorem 8.5, with the ellipsoid method we can solve the linear programming problem that we wrote down a few slides ago in polynomial time. We said that solving that linear programming problem provides a lower bound to the optimal cost of an optimal traveling salesman tour. Therefore, such a lower bound can be computed in polynomial time. If you will take the course integer optimization, you will see that being able to obtain efficiently lower bounds on integer programming problem is of key importance to solve them. With this example, we conclude our discussion on the ellipsoid method. This is also the final video of this course. As always, let me know if you have any question and good luck with the exam.